What if I told you that you could write code that you knew, I mean absolutely knew, was perfect, without running a single test? That sounds kind of wild, right? Well, today we're diving into this really radical idea in programming. What if we built software not by guessing and checking, but through pure, solid mathematical proof?
I mean, think about it. Our usual workflow is, well, you know the drill, right? You write some code, you run the tests, you find a bunch of bugs, you fix them, and you just repeat that whole cycle over and over. It's a loop of hope and repair. But what if that entire way of doing things is just fundamentally flawed? Just imagine, for a second, knowing with total mathematical certainty that your program is correct before you even hit run.
So this is the core idea, the whole game, really, behind a method that was championed by the legendary computer scientist Edgar Dijkstra. It's a complete 180 in how you think about programming. You don't just, type out some code and cross your fingers hoping it's right. No, you construct it piece by piece, like a mathematical proof. You're guaranteeing it's correct from the absolute first step.
All right, so here's the plan. We're going to look at a different way to code, then see how to define the goal mathematically. After that, we'll build a logical model, derive the program loop itself, and then finally, turn all that theory into real working code. And at the end, we'll tackle the big question. Why on earth would you code this way? Okay, let's get into it.
So, first up, a different way to code. The method we're exploring is called program construction, and the key idea here is that a program isn't just something you kind of hack together with trial and error. No, it's something that can be systematically derived from a logical specification, one proven step at a time. Okay, at its heart, this method completely flips the script. You actually start at the end. You define what's called a postcondition, which is just a fancy way of saying a super precise logical statement about what must be true when your program is finished. Then, every single line of code is built backwards from that goal, using proven theorems. The result? A program that is correct by its very design.
All right, the very first step is to take your goal, what you actually want the program to do, and express it with zero ambiguity. And that means we have to leave our normal everyday language behind and switch to the super precise language of mathematics.
So let's start with an idea we can all get our heads around. Just summing up the elements of an array. You take the first one, add the second one, add the third. You just keep going until you hit the end. Pretty simple, right?
Okay, but here's the thing. To build a real proof, we need a language that's way more precise than English. And that entire summation we just talked about, well, in formal logic, it can be expressed in this one single powerful shorthand. This fancy-looking notation lets us say add up all the elements f.i for every index I from 0 up to n with absolutely no room for misunderstanding. And that precision, that's the foundation for everything that comes next. So once our goal is defined with perfect clarity, we still don't start coding. Not yet. Instead, we become logical detectives. Our job is to build what's called a domain model. Just think of this as gathering a collection of proven facts, theorems really, that are all related to our problem. These things become our trusted, unbreakable building blocks for the program.
And look, this isn't some mystical process or a stroke of genius. It's just systematic deduction. First, you solve the absolute simplest version of the problem you can think of. That's your base case. Then you find a rule that lets you solve the next biggest version of the problem. And you just keep repeating that, breaking down the complexity layer by layer until every single piece is a proven, solid, logical fact. Okay, now we get to use those logical building blocks to construct the real engine of our program, the loop. And because we have this formal model all set up, we don't have to guess how the loop should work. We can literally derive it directly from the facts we've already proven. So any formally constructed loop is built on three fundamental pillars. First, there's the invariant. This is a condition that is always true on every single iteration of the loop. Then you have the guard. That's just the check that tells the loop when to stop. And finally, the variant. This is a measure of how much work is left to do, and it has to get smaller each time, which guarantees the loop will actually finish. Now here's the magic. The actual code inside the loop, the part that's doing all the work, it isn't just written on a whim. It is mathematically calculated with one single purpose, to make progress by shrinking that variant, while at the same time rigorously, absolutely maintaining the truth of the invariant. Every single step is logically sound. Okay, we're almost there. With the logical blueprint for our loop totally complete, we have the initial values, the invariant, the guard, the whole shebang. The final stage is just translation.
We now convert this formal proof into a language that a computer can actually understand and execute. So, take a look at this. On the left, you've got the program written in Dijkstra's abstract guarded command language. It's designed specifically for proofs, not for running on a machine. Then on the right, you see that exact same logic translated into a modern functional language like Gleam. The logic is absolutely identical. We're just swapping out the syntax so a real computer can understand what to do.
You know, this quote from Dijkstra really captures the hardcore philosophy behind this whole method. He genuinely felt that if you had a formal proof, then testing was not only unnecessary, it was actually a distraction from true mathematical rigor. For him, the proof is the guarantee, not some test suite.
Okay, so let's pull back a bit and talk about the practical side of things. I mean, this is clearly a super rigorous process. So the big question is, when would you actually want to use it?
Well, the trade-offs here are pretty stark. On the one hand, you get an absolute ironclad guarantee of correctness. That's essential for high-stakes critical software, think aviation or medicine. But on the other hand, it requires a really steep learning curve and a huge upfront investment in just getting the logic right. And yeah, the resulting code is often very concise, but the process prioritizes correctness above everything else, and that sometimes includes raw performance.
But maybe the most fascinating insight from people who actually use this method is this. Once you've defined your goal, the whole process stops feeling like creative coding. You're not making clever design choices or taking inspired guesses. You are simply following the rules of logic, step by step, until the program basically reveals itself. A lot of the time, there's only one logical way it could have ended up.
And this brings us to a really crucial question, especially for the future. In an age where AI is generating more and more code that we humans might not even fully understand, is the power to mathematically prove that code is correct more valuable than ever before? Maybe, just maybe, the future of reliable software lies in rediscovering the pure logic of the past. Something to think about. Thanks for watching.